Imagine waking up one morning to discover that our very nearest sun-like neighbor might be hiding a world. Not a tiny rocky speck, but a full-blown gas giant. The kind of planet that makes headlines because it changes how we think about what S next door. That S exactly the story astronomers landed this month. New James Webb observations have revealed a faint point of light near Alpha Centauri A that looks an awful lot like a Saturn-mass planet orbiting roughly where liquid water could exist on a moon, the so-called habitable zone. If it's real, it would be the closest directly imaged world beyond our solar system. But before we fill our telescopes with fantasy, let's step through the discovery the way the scientists did. Cautiously, with instruments and subtraction algorithms, and a long list of ifs. Webb's mid-infrared instrument, MIRI, used a coronagraph to block the glare of Alpha Centauri A and revealed a faint point-like source in August 2024. The signal survived initial checks and reprocessing, and when researchers compared it to models, the object's brightness and separation from the star were consistent with a Saturn-mass gas giant sitting roughly 1 to 2 astronomical units from Alpha Centauri A, a sweet spot that in our solar system would sit near Earth's orbit. That combination of proximity and brightness is exactly what astronomers dream of, a candidate close enough that follow-ups could actually probe its atmosphere and, if it has them, large moons. Yet the plot thickens. The candidate, given names like S1 or informally Alpha Centauri AB in different write-ups, has played a bit of cosmic hide-and-seek. Follow-up attempts in early 2025, repeat coronagraphic imaging in February and April, failed to recover the source. That disappearance isn't necessarily a death knell. In fact, researchers have plausible reasons for expecting the object to vanish and reappear depending on its orbit and our viewing geometry. A planet on an eccentric path or one currently hidden behind the star AS glare can be invisible for months. The team expects it might become visible again in 2026 or 2027 as orbital motion moves it back into Webb AS line of sight. In short, the candidate S vanishing act makes the hunt both harder and strangely more believable. Planets move. So why would a Saturn-like planet in Alpha Centauri's habitable zone matter so much? For starters, proximity changes the game. At roughly 4.3 light-years away, Alpha Centauri is within reach, in a scientific sense, of instruments we already have, and it's a prime target for next-generation direct imaging and space mission concepts. A near neighbor lets us contemplate studies that would be impossible for distant exoplanets. High-signal atmospheric spectroscopy, searches for moons, and precise orbital characterization that would let us test formation theories right next door. It is the difference between reading a paragraph about a distant city and walking down its main street. That said, the detection itself sits atop a series of hard technical challenges. Imaging a faint planet close to a bright star is like trying to spot a firefly next to a searchlight from thousands of miles away. Webb's coronagraph suppresses the starlight, but residual light, diffraction patterns, instrumental noise, and the system's own zodiacal dust can masquerade as planets. In this case, the team had to subtract both Alpha Centauri A's glare and the contaminating light from its companion star, Alpha Centauri B, a tricky mathematical operation when the stars are bright and close together. That's one reason why independent confirmation with different instruments and at different wavelengths is essential before any cautious language becomes confident discovery language. Let's examine the plausible physical explanations for the observed signal. The simplest and most exciting is that it's a bona fide planet, a gas giant roughly the size and mass of Saturn orbiting at about 1-2 AU. Another possibility is that the point source is an unrelated background object, a distant, faint galaxy or brown dwarf, coincidentally aligned with Alpha Centauri A from our perspective. A third explanation is that what looks like a point source is actually a clump of warm dust, a patch of zodiacal material heated by the star and bright in the mid-infrared. The researchers ran models to rule out the most likely false positives, and the balance of evidence favors a planetary interpretation. But it's not decisive yet. That's why the language in official releases carefully says candidate, or new evidence, not confirmed planet. If the planetary interpretation holds, what could we do next? The first goal is confirmation. Repeated imaging at multiple epochs and wavelengths to show consistent motion and spectral behavior. Ground-based telescopes with extreme adaptive optics, the new class of extremely large telescopes, ELTs, coming online, and space observatories like the Nancy Grace Roman Space Telescope could provide crucial follow-ups in the next few years. Spectroscopy of a nearby gas giant could reveal molecular fingerprints, methane, ammonia, and perhaps unexpected chemistry. And if the planet has rings or big moons, those signatures might be teased out too. A moon the size of Mars could, in principle, have conditions very different from the gas giant and would become an irresistible target for astrobiology, though detecting exomoons is notoriously difficult. Still, the mere possibility of habitable moons around a nearby gas giant is the stuff of science fiction meets science fact headlines. Beyond the immediate observational follow-ups, there are broader scientific payoffs. Alpha Centauri is a triple system, 2 sun-like stars in a binary, A and B, plus the red dwarf Proxima, farther out. We already know Proxima hosts at least 3 planets, including one in its temperate zone. Finding a gas giant around Alpha Centauri A would reshape our understanding of how multi-star systems build planetary systems. Did the presence of sibling stars shepherd material in ways that favor gas giant formation? Does multiplicity influence the architecture and habitability of a system? Nearby giants can also act as dynamic architects, stirring or shepherding smaller bodies and influencing the likelihood and history of impacts on interterrestrial worlds. In short, a confirmed planet here would become a Rosetta Stone for comparative planetology. Let's be frank about expectations. The astronomy community has seen many tantalizing signals that didn't pan out: instrumental artifacts, misidentified background sources, or statistical flukes. The responsible approach is skeptical curiosity, celebrate the extraordinary dataset Webb provided, but require the ordinary scientific steps of independent verification and reproducibility. This candidate's pattern, spotted, not seen again, then reanalyzed, actually fits the model of an orbital object more than some one-off glitch. Planets move. Speckles and dust do not move in an orbital pattern. Upcoming observations timed by orbital predictions will be the make-or-break moments. One of the quiet, important takeaways from this episode is how much our tools have improved. 20 years ago, imaging a planet this close to its star at these wavelengths would have been science fiction. Webb's stability, sensitivity, and coronagraphic capability combined with modern data processing algorithms make these hunts practical. But these are still early days in the era of direct imaging, and each candidate, whether confirmed or refuted, teaches us how to build better instruments, devise smarter subtraction algorithms, and plan more effective observing campaigns. The technological curve is steep, and we're riding it live. Now consider the cultural and philosophical angle. The Alpha Centauri system has always occupied a special place in the human imagination. The nearest star system, the natural destination of our dreams for interstellar probes and first contacts. If there is a Saturn-like planet with moons in the habitable band, it instantly becomes not just scientific data, but a narrative magnet. Science will properly be cautious, but the public will naturally begin to ask, could life arise on a moon? What would it take to visit? How would our place in the cosmos feel different knowing that a complex planetary system sits so nearby? Those questions mix wonder and pragmatism, and they drive funding, missions, and the next generation of explorers. We should also talk about the time scale. Even if this is a confirmed planet, getting a detailed picture, spectra, orbital dynamics, any moons, will take years. The Roman telescope, ELTs and other platforms will chip away at the candidate's properties in the late 2020s. Direct robotic exploration remains a much longer prospect. Even the fastest theoretical interstellar probes would take decades to reach Alpha Centauri, and anything crewed remains in the realm of distant plans. In the near term, the reward is purely scientific, a nearby laboratory to test planet formation, and atmosphere models with far better signal-to-noise than typical exoplanets hundreds or thousands of light-years away. There is one last scientific twist worth noting. The object's mid-infrared brightness was a touch brighter than pure planet models predicted. That's a clue with multiple interpretations. It could mean the planet is unusually reflective, has a larger radius, sports a ring system that increases its cross-section, or exists in a local patch of dust that adds mid-IR glow. Each of those options carries different implications for formation history and for how we interpret follow-up data. Part of the excitement and the headache of this discovery is that the signal is rich with possible stories. Teasing which story is true will be a months to years project. So where does this leave us tonight? As viewers and curious citizens of a planet orbiting a modest, ordinary star, it leaves us watching, patiently. Science drips detail into headlines only after long stretches of careful measurement. For now, the announcement is a call to arms for astronomers. Schedule telescope time, run the subtraction algorithms, model the orbit, and convince the skeptical reviewers that this point of light is a moving world and not a masquerade. If you want to follow the technical trail, read the Webb team's release and watch for data from independent instruments. The living story will unfold in plots, spectra, and boxed figures rather than instant proclamations. If you like this deep dive, here's a small favor that helps us keep doing this work. Subscribe, hit the bell, and share this episode with someone who loves big cosmic mysteries. Tell me in the comments which angle you want next. A layman's explainer on coronagraphy, a technical walkthrough of how astronomers subtract starlight, or a speculative episode on what life on a moon around a gas giant might look like. I'll pin the best suggestion and build it into our follow-ups. Tonight's takeaway is simple but thrilling. Webb has shown us a faint new light near our closest stellar neighbor that behaves in all the important ways like a planet. We don't yet know its name, its rings, or whether it hides moons. We only know that the next few years of careful astronomy will either confirm a nearby new world, and with it open a fresh laboratory for planetary science, or teach us valuable lessons about how to separate planets from noise. Either outcome moves the frontier. Either outcome is worth the watch.